Hi everyone, my name is Linlin. I'm a PhD candidate from the latest lab in Sahuang, Normandie University, supervised by Professor Benoit Honeine and Professor Benoit Gaüzère. Today I will present our work, a graph pre-image method based on graph edit distances. In recent years, more and more datasets has been modeled by graphs because of its expressive structure. However, this expressive comes with a cost. There is a gap between the graph data and the machine learning methods. So, how to bridge this gap? There are many proposed methods. One of the most widely used and studied is the graph kernel. Graph kernel implicitly maps a graph into a kernel space. The inner product between elements in the kernel space can be computed directly by graphs, namely the kernel trick. With the graph kernels, many common machine learning methods can be used on graphs. When we have a point in the kernel space, an interesting question is, how do we construct a graph corresponding to that? This is the so-called pre-image problem. Its application includes image reconstruction, molecule synthesis, and drug designs, etc. There has been some methods proposed to construct graphs. One of them is based on iterations. This method operates on kernel space. However, it is restricted to inserting and removing edges, and the number of these operations is also limited. Moreover, only random constructions can be considered, which means this method cannot guarantee quality and time complexity. And no labeling information can be added. Another set of methods is based on graph edit distance, namely the GED. It is a natural way to construct graphs. However, it is only explore the graph space, which is not a pre-image method. Based on this, we propose an iterative graph pre-image methods which use GEDs as a direction to construct graph. There are many kinds of graph kernels. A widely used one is based on substructures. There are linear patterns. Non-linear patterns serve as substructures. We measure similarities between pairs of patterns, and graph kernels between two graphs is constructed on these comparisons. To construct graphs, we use a graph edit distance. To transform one graph to another, 6 fundamental operations can be used, namely the insertion, removal, and substitution between nodes and edges. The sequence of these operations composed of an edit path denoted by pi. Each operation is associated with a cost, which measures the distortion of these operations. And the cost of pi is the sum of the costs of these associated operations. The GED between two graphs is then equals to the minimum costs of pi's. We denote the cost of operations by the vector c, and the numbers of occurrences of each operation by the vector omega, and the GEDs between two graphs can be rewritten as a multiplication of these two vectors. To construct pre-image, we first need to align the graph space and kernel space by matrix learning. We want the distance between each pair of graphs to be as close as possible to the distance between the corresponding elements in the kernel space. Namely, we want D1 equals to df1, D2 equals to df2, and so on. Here in the graph space, we use GED to measure the dissimilarity, and in the kernel space, the distance can be computed by the kernel functions. Now, This problem boils down to minimization between the differences of these two distances over all pairs of graphs. However, when the vector c changes, the corresponding edit path and the vector omega also changes, so this optimization cannot be solved directly. We propose an alternative iterative optimization strategy. Each iteration consists of two steps. In step 1, we fix the vector c and we use the heuristics to compute GED, the edit passes, and the corresponding vector omega. We form the vector omega between all pairs of graphs into a matrix W. In step 2, we fix the matrix W to optimize C, and the minimization problem can be now considered as a constrained linear optimization problem, where the classic solver can be used. We continue this procedure until the optimized cost C is obtained. Now we have the optimizer C. How do we construct preimage? We take advantage of a recent method which constructs media graph. Here we also use an alternative iterative procedure with two steps. In each iteration, in step 1, we fix the media graph and compute the GED between media graph and all graphs in the dataset. In step 2, we fix the corresponding edit passes and we use a block coordinate update procedure to update the media graph. Each node in the graph is replaced by another node based on the edit passes. The label of the node is replaced by the most occurred label over these nodes. The edge is updated the same way. Next, we conduct experiments to test our method. The dataset letter is used. This is a dataset of handwriting letters with different distortions. The node of these letters have non-symbolic labels, which is the coordinates. We use bipartite and IPFP heuristics to compute the GED, where the M represents a multi-start counterpart of the heuristics, and the M is equal to 40. The size of the media set is set to 150. The number of parallelized job is set to 28. This table shows the distance in kernel spaces. We compare our methods with 3 others, and the best performance is marked with a bold font. We can see that our method achieved one of the best performance in most cases, which is competitive to the expert costs. Here we show the preimage generated by each method for the letter high dataset. Our method is marked with a green color. We can see that our method is the most eligible among all the methods. So, in conclusion, in this work we proposed a novel method to estimate graph preimage by aligning kernel space and graph space using a matrix learning method. The experiment shows that our method generates better preimages than other methods. The future work includes constructing the preimage as arbitrary graphs except for just the media graph. And we will also establish convergency proof for our optimization procedure. It will be also interesting to extend our method to graphs with symbolic labels and to non-constant costs. And that would be all. Thank you very much. Any questions?